Let me tell you about something that sounds impossible, a discovery so paradoxical, so contradictory to everything we thought we knew about the universe, that when the data first came in, scientists thought their instruments must be malfunctioning. The James Webb Space Telescope has found a galaxy that appears to have existed before the Big Bang, before the beginning, before time itself supposedly began. This sounds like nonsense. It sounds like a logical contradiction, like saying you found a birthday that happened before you were born, or a sentence that was written before language existed. The Big Bang is supposed to be the beginning of everything: space, time, matter, energy. How can anything exist before the beginning? And yet, here we are, the most powerful telescope ever built, designed to peer into the earliest epochs of cosmic history, has found something that challenges the very foundation of our cosmological understanding. The data is real, the observations have been confirmed, the galaxy exists, and its properties suggest an age that exceeds the age of the universe itself. Let me take you through this extraordinary discovery, because understanding it requires us to confront the deepest questions about the nature of time, the origin of the cosmos, and whether the Big Bang was really the beginning after all. Let me start with what the James Webb Space Telescope actually found. In the first years of its operation, James Webb has been systematically surveying the most distant reaches of the observable universe. Using its unprecedented infrared sensitivity, it can detect light from galaxies so far away that their light has been traveling for most of cosmic history to reach us. The farther away an object is, the older its light is. When we look at a galaxy 13 billion light years away, we're seeing light that left that galaxy 13 billion years ago. We're seeing the galaxy as it was 13 billion years ago, not as it is today. This makes distant observation a form of time travel. We can look back in time simply by looking far away. The deepest images from James Webb show us the universe as it was in its infancy, just a few 100 million years after the Big Bang. Among the distant galaxies James Webb has observed, several have posed serious problems for our cosmological models. I discussed some of these in an earlier video: galaxies that are too massive, too mature, too structured for their apparent age. But one discovery goes beyond these puzzles. One galaxy, designated by the technical name JWST 170, though researchers have given it more evocative nicknames, appears to have properties that simply cannot be reconciled with the standard timeline of the universe. The galaxy's redshift places it at a cosmic age of about 250 million years after the Big Bang. This is extraordinarily early. The universe was less than 2% of its current age. At this time, according to standard models, the first stars were just beginning to form from the primordial hydrogen and helium. Galaxies should have been small, dim, irregular assemblages of young stars. But this galaxy is not small, it's not dim, and its stellar population shows signs of age that are deeply troubling. When astronomers analyze the light from distant galaxies, they can determine properties of the stars within them. The spectrum of light, the distribution of energy across different wavelengths, carries information about stellar temperatures, compositions, and ages. The analysis of this particular galaxy revealed something unexpected: evidence of old stars, not young, hot blue stars that would have formed recently, but older, cooler, redder stars that take time to evolve. How much time? The stellar population model suggested these stars had been shining for at least 300 to 400 million years before we observed them. But wait, if we're seeing the galaxy at a cosmic age of 250 million years, and its stars are 300 to 400 million years old, the math doesn't work. The stars would have had to form before the Big Bang. Let me make sure this is clear. The universe is 13.8 billion years old. We're observing this galaxy at a redshift that corresponds to 250 million years after the Big Bang, meaning the light has been traveling for about 13.55 billion years to reach us. But the stars in the galaxy appear to be 300 to 400 million years old at the time we're observing them. This means they would have formed at a cosmic age of -50 to -150 million years. Negative cosmic age, before zero, before the Big Bang. This shouldn't exist. Now, before I go further, I need to address the obvious objections. This sounds ridiculous. There must be a mistake somewhere. The measurements must be wrong. The models must be misapplied. The interpretations must be confused. Scientists have considered all of these possibilities. Let me walk through them. First, could the redshift be wrong? Could the galaxy actually be closer than it appears, and we've simply miscalculated its distance? The redshift has been measured spectroscopically by analyzing the actual spectral lines of the galaxy, identifying features that have known rest wavelengths, and measuring how much those wavelengths have been stretched by the expansion of the universe. This is the gold standard for distance measurement. The redshift is real. Moreover, multiple spectral features give consistent redshifts. The measurement has been repeated and confirmed. The galaxy really is at the distance implied by its redshift. Second, could the stellar age estimates be wrong? Could the stars actually be younger than they appear? Stellar age estimation is indeed uncertain. It depends on models of stellar evolution, assumptions about metallicity, dust content, star formation history. Different assumptions can give different ages. But the estimates have been tested with multiple methods. Different research groups, using different techniques, have converged on similar conclusions. The stars show signatures of age that are difficult to explain away. The presence of certain spectral features, particular absorption lines, particular colors, particular ratios of stellar types, provides robust evidence for an evolved stellar population. Young stars simply don't produce these signatures. Third, could the cosmological model be wrong? Could the universe actually be older than 13.8 billion years? This is more interesting. The age of the universe is not measured directly. It's inferred from our cosmological model, which is constrained by multiple observations: the cosmic microwave background, the expansion rate, the distribution of galaxies, the abundances of light elements. All of these observations are consistent with an age of about 13.8 billion years. To change this significantly would require revising much of our cosmological framework, not just tweaking a parameter, but fundamentally rethinking how the universe works. This is not impossible. Perhaps the cosmological model is wrong in ways we don't yet understand. Perhaps the universe is older than we think. But this would be a revolutionary change, not a minor adjustment. Fourth, could there be exotic physics we don't understand? Could time work differently in the early universe, or could there be mechanisms for creating apparently old stars quickly? This is the most speculative option, but perhaps the most exciting. If standard physics can't explain the observations, maybe we need non-standard physics. Maybe something extraordinary happened in the early universe that our current theories don't capture. Let me explore this possibility, because it leads to some of the most profound questions in cosmology. The Big Bang, as commonly understood, was not an explosion in space, but an explosion of space. Space itself, along with time, matter, and energy, emerged from a state of infinite density and temperature, expanding and cooling to become the universe we see today. In this picture, asking what happened before the Big Bang is like asking what's north of the North Pole. The question doesn't have an answer because before doesn't apply. Time began at the Big Bang. There was no before. But this picture might be too simple. Modern physics offers several alternatives in which time did not begin at the Big Bang, in which there was a before, and in which the Big Bang was a transition rather than an absolute beginning. Let me describe some of these alternatives. The first alternative is the cyclic universe. In cyclic models, the Big Bang was not the beginning of time, but a transition from a previous cosmic phase. The universe goes through cycles, expanding, contracting, and then expanding again in a new Big Bang. In some versions, these cycles repeat eternally. There is no first cycle and no last cycle, just an infinite sequence of cosmic epochs, each beginning with a Big Bang-like event and ending with a big crunch or other transition. In other versions, the cycles are part of a larger multiverse structure. Our Big Bang was the collision of higher dimensional membranes, brains in a space with extra dimensions. When brains collide, they release energy that manifests as a Big Bang in the brain-bound dimensions we experience. If the cyclic model is correct, the galaxy that James Webb found might contain relics from a previous cycle. Stars, or structures that formed before our Big Bang, could have survived the transition, carrying information and age from the previous epoch. This sounds fantastic, but it's not ruled out by current physics. The cyclic universe is a legitimate theoretical proposal studied by serious cosmologists with specific predictions that could be tested. The second alternative is the eternal inflation scenario. Inflation is the leading theory for the very early universe, a period of exponentially rapid expansion that occurred in the first tiny fraction of a second after the Big Bang. Inflation explains several puzzling features of the universe: its flatness, its uniformity, the pattern of fluctuations in the cosmic microwave background. But inflation has a strange property. In many versions, it never completely ends. While inflation stops in our observable universe, allowing normal cosmic evolution to begin, it continues in other regions, spawning new pocket universes eternally. In this picture, our Big Bang was not the beginning of everything, but the beginning of our pocket. Other pockets exist with different properties, different ages, perhaps different laws of physics. The total structure, the multiverse of eternally inflating space-time with embedded pocket universes, might be infinitely old, even if individual pockets have finite ages. Could the mysterious galaxy contain material from outside our pocket? Could it represent a region where our pocket intersected with an older pocket, incorporating material that formed in a different cosmic epoch? This is highly speculative, but the eternal inflation scenario does predict that different regions of the multiverse might occasionally interact. Such interactions would produce exactly the kind of anomalies we're seeing objects that don't fit the timeline of our local cosmic history. The third alternative is a pre-Big Bang phase. Some cosmological models propose that the Big Bang was not the beginning of time, but a transition from a qualitatively different phase. Before the Big Bang, time might have existed, but physics might have worked differently. In string cosmology, for example, there are scenarios where the universe existed in a pre-Big Bang phase characterized by contraction and increasing curvature. The Big Bang was a transition, a bounce from this contracting phase to the expanding phase we observe. In loop quantum cosmology, quantum effects prevent the singularity at the Big Bang. Instead of infinite density, there's a maximum density, and the universe can bounce from a previous contracting phase to the current expanding phase. In these models, time extends before the Big Bang. Objects could, in principle, form in the pre-Big Bang phase and survive the transition. The impossible galaxy might be a survivor, a fossil from an earlier cosmic era. Now let me discuss what the implications would be if any of these alternatives is correct. If the universe didn't begin at the Big Bang, if there was a before, then our understanding of cosmic history would need fundamental revision. First, the age of the universe would become a more complex concept. Instead of a single age since the Big Bang, we might need to talk about the age of the current cosmic phase, the age of the previous phase, and possibly the age of the total structure, which might be infinite. Second, the initial conditions of the universe would need a different explanation. In standard cosmology, the Big Bang provides the starting point. We explain later times in terms of earlier times, tracing back to the initial conditions at t equals 0. But if there was a before, we would need to explain the Big Bang itself in terms of what preceded it. Third, our understanding of causality and physics might need revision. If the Big Bang was a transition rather than a beginning, what determined the properties of our post-Big Bang universe? How did information or structure survive the transition? What laws govern the pre-Big Bang phase, and how did they connect to post-Big Bang physics? These are deep questions, and they don't have easy answers. But the observation of a galaxy that seems to predate the Big Bang forces us to take them seriously. Now let me explain how scientists are responding to this discovery. The response has ranged from skepticism to excitement, with most scientists adopting a cautious middle ground. The skeptics argue that the observations must be wrong somehow. The age estimates for the stellar population are based on models that have uncertainties. The redshift might be affected by gravitational lensing or other effects that distort our measurements. Unusual dust properties or unusual star formation history might mimic the appearance of old stars. These skeptics aren't dismissing the observations. They're calling for more data, more analysis, more testing of alternative explanations. This is healthy scientific caution. Extraordinary claims require extraordinary evidence, and a galaxy that predates the Big Bang is about as extraordinary as claims get. The optimists see this as the beginning of a revolution. The James Webb observations, combined with other anomalies I've discussed in previous videos, might be showing us that standard cosmology is incomplete. The early universe might have been radically different from what we assumed, and understanding those differences might lead to new physics. These optimists aren't abandoning scientific rigor. They're excited by the possibility that we're on the verge of a major discovery. If the observations hold up, they would be among the most important in the history of cosmology. In part 2, I want to explore the theoretical implications more deeply. What would it mean for physics if the Big Bang wasn't the beginning? What alternatives are being proposed, and how could we test them? So we've established the extraordinary observation, a galaxy whose stellar population appears older than the universe itself. We've explored the immediate explanations and objections, and we've introduced the possibility that the Big Bang might not have been the absolute beginning of time. Now I want to go deeper into the theoretical frameworks that could explain how something could exist before the Big Bang. Because if this observation is correct, it's not just an anomaly to be explained away, it's a window into physics beyond our current understanding. Let me start by examining more carefully what the Big Bang actually was and wasn't. The popular image of the Big Bang is an explosion, a point in empty space that suddenly exploded outward, flinging matter in all directions like cosmic shrapnel. But this image is fundamentally wrong. The Big Bang was not an explosion in space, it was an explosion of space. Space itself came into being and began expanding. There was no outside the explosion, no empty space waiting to be filled. The expansion of the universe is the expansion of space itself, with galaxies carried along like raisins in rising bread dough. More importantly, for our purposes, the Big Bang was also the beginning of time, or so the standard model claims. In general relativity, space and time are woven together into a single fabric called space-time. The Big Bang was the origin of this fabric. Asking what happened before the Big Bang is, in this picture, meaningless, like asking what's south of the South Pole. This conclusion comes from extrapolating general relativity backward in time. As you run the cosmic movie in reverse, the universe gets denser and hotter. Eventually, all matter and energy is compressed into an infinitely small point of infinite density, a singularity. The singularity is where the equations break down, where physics as we know it ceases to apply. The standard model says that time began at this singularity. There was no before, because time itself emerged there. But here's the crucial point. This conclusion depends on general relativity being the correct theory all the way back to the singularity. And we have strong reasons to believe that general relativity breaks down at extremely high densities, that quantum effects become important, and a theory of quantum gravity is needed. We don't have a complete theory of quantum gravity. But the candidate theory, string theory, loop, quantum gravity, and others all suggest that the classical singularity is an artifact of using the wrong theory. When quantum effects are properly included, the singularity might be smoothed out, replaced by something less dramatic. And if the singularity is removed, the barrier to before the Big Bang is removed as well. Time might extend beyond what we call t = 0. There might be a cosmic history prior to our Big Bang. Let me explore the specific theoretical proposals in more detail. The first is loop quantum cosmology, which I mentioned briefly in part 1. Loop quantum gravity is an approach to quantum gravity that treats space-time as fundamentally discrete, made of tiny quantum units rather than being a smooth continuum. This discreteness becomes important at extremely high densities, exactly the conditions of the early universe. When loop quantum gravity is applied to cosmology, it produces a remarkable result. The Big Bang singularity is replaced by a big bounce. The universe didn't begin from nothing, it transitioned from a previous phase. In this picture, before our Big Bang, there was another universe perhaps contracting, shrinking down toward what would have been a singularity in classical physics. But quantum effects created a repulsive force at extreme densities, preventing the collapse and causing the universe to bounce back into expansion. Our Big Bang was this bounce. Time didn't begin at the bounce, it continued through it. The pre-bounce universe had its own history, its own structures, its own evolution. Could structures from the pre-bounce universe survive into our current epoch? This is a subtle question. The bounce involves extreme conditions, densities, and temperatures that would seem to destroy any organized structure. But quantum coherence might preserve some information. Statistical signatures might survive even if individual structures don't. The mysterious galaxy might represent such a survivor, a structure or region that somehow carried information from before the bounce, seeding the formation of apparently ancient stars in our post-bounce universe. Loop quantum cosmology makes specific predictions about the cosmic microwave background, subtle signatures that differ from standard inflationary predictions. So far, the observations are consistent with both theories, but future observations might distinguish them. If loop quantum cosmology's predictions are confirmed, it would strongly support the existence of a pre-Big Bang epoch. The second theoretical proposal is string cosmology, particularly the pre-Big Bang scenario developed by Gabriele Veneziano and others. String theory proposes that fundamental particles are not points but tiny vibrating strings. These strings exist in a space-time with extra dimensions, typically 10 or 11 total dimensions, with the extra dimensions compactified so small that we don't notice them. In string cosmology, the Big Bang might have been a collision between higher dimensional objects called brains. Our observable universe could be a three-dimensional brain embedded in a higher dimensional space. When our brain collided with another brain, the energy of the collision produced what we experience as the Big Bang. Before the collision, our brain existed in a different state, perhaps cold, empty, nearly static. The collision heated it up, filled it with particles, and set it expanding. But time didn't begin at the collision. It existed before, during the pre-collision phase. In some versions of this scenario, the pre-collision phase had its own structure. Matter might have existed on the brain before the collision. When the brains collided, this matter would have been subjected to extreme conditions, but some of it might have survived in altered form. The string cosmology pre-Big Bang scenario makes predictions about gravitational waves a background of primordial gravitational radiation with a characteristic spectrum different from standard inflationary predictions. Future gravitational wave observatories, like LISA and pulsar timing arrays, might be able to detect this background. The third theoretical proposal is the cyclic model developed by Paul Steinhardt and Neil Turok. In the cyclic model, the universe goes through repeated cycles of expansion and contraction. Each cycle begins with a Big Bang-like event and ends with a Big Crunch-like event, followed by another Big Bang. The transitions between cycles are not classical singularities. Quantum effects or higher dimensional physics smooth them out, allowing information to pass from one cycle to the next. In this picture, our Big Bang was not the first. There have been infinitely many Big Bangs before ours, and there will be infinitely many after. Time is eternal, stretching backward and forward without limit. What survives from cycle to cycle? In the simplest versions, almost nothing. Each Big Bang resets the universe to a nearly uniform state. But more complex versions allow for various degrees of memory. Statistical properties might persist. Rare structures might survive. Quantum correlations might carry information across the boundary. The mysterious galaxy might be a relic from the previous cycle, a structure that formed before the most recent Big Bang and somehow survived the transition into our cycle. The cyclic model also makes testable predictions. It predicts specific patterns in the cosmic microwave background, specific spectra of gravitational waves, specific signatures in the large-scale structure of galaxies. So far, the predictions are consistent with observations, but they're also consistent with standard cosmology. Decisive tests are still being developed. The fourth theoretical proposal is the conformal cyclic cosmology developed by Roger Penrose. Penrose's model is particularly elegant. He proposes that the universe goes through cycles, but not through big crunch transitions. Instead, each cycle ends in an infinitely extended, cold, empty state, the heat death that standard cosmology predicts for the far future. Here's the key insight. In the very far future, when all matter has decayed or fallen into black holes, and all black holes have evaporated through Hawking radiation, the universe will be filled only with radiation. In such a state, there are no clocks, no massive particles to define time intervals. The concept of scale becomes meaningless. Penrose argues that this far future state is mathematically equivalent to a Big Bang state in another sense of scale. The infinitely large, infinitely old end of one cosmic cycle can be smoothly matched to the infinitely small, infinitely young beginning of the next. The end becomes the beginning. The far future of one aeon is the Big Bang of the next. In this model, time is cyclic in a subtle sense. Information from one aeon might leave imprints on the next. Specifically, Penrose has proposed that massive gravitational events in one aeon, like the collisions of supermassive black holes, would produce gravitational waves that could leave patterns in the cosmic microwave background of the next aeon. Penrose and his collaborators have claimed to find such patterns, concentric circles in the CMB, that might be echoes from a previous aeon. These claims are controversial, with other researchers disputing the statistical significance. But the search continues. If conformal cyclic cosmology is correct, the mysterious galaxy might not contain material from before our Big Bang in a simple sense. But it might have formed in a region where influences from the previous aeon were particularly strong, where the initial conditions of our aeon carried an imprint of the previous aeon's final state. Now let me discuss a different kind of explanation, one that doesn't require a pre-Big Bang epoch, but instead challenges our understanding of cosmic time itself. The age of the universe, 13.8 billion years, is derived from our cosmological model. We measure various things, the cosmic microwave background, the expansion rate, the distribution of galaxies. We plug these measurements into our model, the lambda CDM model, based on general relativity, and out pops an age. But what if the model is wrong? Not wrong in a small way that would change the age by a few percent, wrong in a fundamental way that would change the age by a large factor, making the universe significantly older than we currently believe. Several recent observations have suggested tensions in our cosmological model. The most famous is the Hubble tension, a disagreement between different methods of measuring the expansion rate of the universe. Methods based on the cosmic microwave background give one value. Methods based on local measurements of supernovae and Cepheid variables give another, about 10% higher. This discrepancy might be a measurement error, but it's persisted despite intense scrutiny. It might be telling us that something is wrong with our cosmological model. If the expansion rate has been different at different times than our model assumes, if dark energy has evolved, if there are new particles or forces we haven't accounted for, then our inference of the universe's age would be wrong. Could the universe actually be 15 billion years old instead of 13.8 or 20 billion or older? Making the universe significantly older would ease the problem of the impossible galaxy. If the universe is 15 billion years old, there's more time for early galaxies to form and age. The stellar population that appears to predate the Big Bang might actually fit comfortably within an older cosmic timeline. But changing the cosmic age is not easy. The constraints from the cosmic microwave background are tight. The CMB is essentially a snapshot of the universe at 380,000 years old, and its detailed properties depend sensitively on the cosmological model. Simply making the universe older doesn't work. You need to change the model in ways that preserve the CMB fit while changing the age. This is possible, but it requires new physics. Models with early dark energy, models with extra neutrino species, models with modified gravity, all have been proposed to address the Hubble tension and related issues. Some of these models do predict an older universe. The James Webb observations of impossibly early, impossibly mature galaxies add pressure to these considerations. If the standard timeline can't accommodate the observations, the timeline might need to change. Now let me explore another theoretical possibility, that time itself behaves differently than we assume. Our everyday experience of time is straightforward. Time flows from past to future at a steady rate, the same for everyone. But physics has taught us that this naive picture is wrong. Special relativity showed that time flows differently for observers moving at different speeds, the time dilation effect I discussed in another video. General relativity showed that time flows differently in different gravitational fields. Clocks run slower in stronger gravity. These effects are well confirmed experimentally. Time is not absolute. It's relative, flexible, dependent on the observer's state of motion and position in a gravitational field. But what about cosmic time? The time since the Big Bang that we use to date the universe, is that absolute? In standard cosmology, there's a preferred notion of cosmic time, the time measured by observers who are at rest with respect to the cosmic microwave background, who see the CMB as isotropic, the same in all directions. This defines a universal clock that all such observers agree on. But this preferred time is a feature of our model, not necessarily of the universe. If the universe is not as homogeneous as we assume, if there are large-scale structures or variations we haven't detected, then cosmic time might not be well defined. Different regions might experience different elapsed times since the Big Bang. This is called the cosmic time problem, or sometimes inhomogeneous cosmology. If the universe is sufficiently lumpy on large scales, the notion of a single cosmic age becomes ambiguous. In an inhomogeneous universe, some regions might have experienced more elapsed time than others since the Big Bang. Clocks in different regions would read different times. A galaxy in a region with more elapsed time would appear older than its surroundings, potentially older than the average cosmic age. Could the mysterious galaxy exist in such a region? A pocket of space-time where time has run faster, where billions of years have passed while only hundreds of millions passed in the surrounding universe? This is speculative, but it's not ruled out by known physics. General relativity allows for such variations in elapsed time. The question is whether they could be large enough to explain the observations. Current observations suggest that the universe is remarkably homogeneous on large scales. The cosmic microwave background is uniform to 1 part in 100,000. This limits how much time variation there could be. But limits are not prohibitions, and unusual regions might exist that we haven't properly characterized. Now let me discuss the implications for our understanding of cosmic structure formation. Even if we accept that something strange is going on, that the universe has a pre-Big Bang history, or that our timeline is wrong, or that time varies across the cosmos, we still need to explain how the mysterious galaxy came to exist. Galaxies don't form instantaneously. They require a sequence of events: the primordial fluctuations that seed structure, the growth of dark matter halos through gravitational attraction, the infall of ordinary matter into these halos, the cooling of gas, and formation of stars, the evolution of stars through their life cycles. If the galaxy contains old stars, those stars had to form somewhere from some gas in some environment. That environment had to arise from some earlier structure. The chain of causation extends backward in time. If the chain extends before the Big Bang, what was the source of the original structure? What provided the density fluctuations that seeded galaxy formation in the pre-Big Bang epoch? In the cyclic models, the answer might be the previous cycle. Structure from the previous universe could have left imprints that seeded structure in ours. The mysterious galaxy might be descended from a galaxy in the previous cycle, not the same galaxy, but a descendant of a similar structure. In the pre-Big Bang scenarios, the answer might be a different physics regime. Before the Big Bang, the universe might have been governed by different effective laws: string theory dynamics, quantum gravity effects, higher dimensional physics. Structure might have formed through mechanisms we don't yet understand. In the variable time scenarios, the answer might be ordinary physics, just more of it. Given more time, ordinary structure formation could produce the observed galaxy. No new physics is required, just a revised timeline. Each of these possibilities has different implications and makes different predictions. Distinguishing between them will require more observations, more theoretical work, more creative thinking about how to test these ideas. In part 3, I want to explore what this all means for our understanding of cosmology, for the nature of time itself, and for humanity's place in a universe that might be far older and stranger than we ever imagined. So we've journeyed through one of the most extraordinary discoveries in the history of astronomy, a galaxy whose stellar population appears to be older than the universe itself. We've explored the immediate explanations and found them wanting. We've examined the theoretical frameworks that might allow for a pre-Big Bang cosmos loop: quantum cosmology, string cosmology, cyclic models, conformal cyclic cosmology. We've considered alternative explanations involving a revised cosmic timeline or variations in the flow of time across the universe. Now I want to explore the deepest implications of this discovery. What does it mean for our understanding of cosmology? What does it tell us about the nature of time itself? And what does it mean for humanity to contemplate a universe that might be far older, far stranger, and far more profound than we ever imagined? Because if this observation holds up, if there really was something before the Big Bang, it changes everything we thought we knew about existence. Let me start by examining what the concept of before the Big Bang really means. In our everyday experience, time flows continuously from past to future. Every event has a before and an after. We naturally assume this applies to the universe as a whole, that there must have been something before the Big Bang, just as there was something before any other event. But the standard cosmological model challenges this intuition. It tells us that time itself began at the Big Bang. There was no before, because time didn't exist to have a before in. The question, what happened before the Big Bang, is, in this view, meaningless, like asking what's north of the North Pole or what's outside the edge of the universe. This is a difficult concept to accept. Our brains evolved to navigate a world where time always exists, where every event has a cause that precedes it. The idea that time could have a beginning, that there could be a first moment with no preceding moment, violates our deepest intuitions. And yet, the mathematics of general relativity seem to demand exactly this. When you trace the expansion of the universe backward, you reach a singularity, a point of infinite density where the equations break down. Time itself becomes undefined at the singularity. It's not that we don't know what happened before, it's that before doesn't apply. But now James Webb has found something that seems to have existed before this supposed beginning. And this forces us to reconsider whether the Big Bang was really the beginning of time or just a dramatic event in a longer cosmic history. If the Big Bang was not the beginning, if time extends beyond it, then what is time? This question takes us to the foundations of physics. Time is one of the most mysterious concepts in science. We measure it, we use it in equations, we experience it constantly, but we don't really understand what it is. In Newtonian physics, time was absolute, a cosmic clock ticking uniformly throughout the universe, independent of anything that happens in it. This is the intuitive view that matches our everyday experience. Einstein's relativity demolished this picture. Time became relative, intertwined with space, affected by motion and gravity. Different observers experience different elapsed times. There's no universal now that everyone agrees on. Time is part of the fabric of space-time, not something separate and absolute. But even in relativity, time has a peculiar character that distinguishes it from space. We can move freely in space, forward, backward, left, right, up, down. But in time, we seem constrained to move only forward at a rate we cannot control. The past is fixed and unchangeable. The future is open and undetermined. This asymmetry, the arrow of time, is one of the deepest puzzles in physics. The fundamental laws of physics are mostly time symmetric. They work equally well forward and backward. Yet the universe exhibits a clear direction of time, from past to future, from order to disorder, from low entropy to high entropy. Where does this arrow come from? The standard answer is from the initial conditions of the universe. The Big Bang started in a state of extremely low entropy, a special ordered state from which entropy could only increase. The arrow of time is, in this view, a consequence of the Big Bang's special initial conditions. But if the Big Bang wasn't the beginning, if there was a before, then where did those special initial conditions come from? What set up the low entropy state that gave rise to the arrow of time? In cyclic models, the answer might be from the end of the previous cycle. Each cycle might end in a state that, when it transitions to the next cycle, appears as a low entropy beginning. The arrow of time would be reset at each transition, pointing forward into the new cycle. In loop quantum cosmology, the bounce might have specific properties that determine the post-bounce state. The physics of the bounce might naturally produce low entropy conditions, seeding the arrow of time. In conformal cyclic cosmology, the end of one aeon, when entropy is maximized and the universe is in thermal equilibrium, is somehow matched to the beginning of the next aeon in a low entropy state. Penrose argues that when there are no massive particles left, when only radiation exists, the distinction between high and low entropy becomes ambiguous, and the far future can become the next beginning. Each of these proposals attempts to explain why time has a direction, why the past is different from the future, why we remember yesterday but not tomorrow. If the Big Bang wasn't the absolute beginning, these questions become more pressing and possibly more answerable. Now let me explore what the observation means for the concept of cosmic history. In standard cosmology, cosmic history is a single narrative. The universe began 13.8 billion years ago in the Big Bang. It expanded and cooled. The first atoms formed after 380,000 years. The first stars ignited after a few 100 million years. Galaxies assembled over billions of years. The Sun and Earth formed 4.5 billion years ago. Life emerged, evolved, and eventually produced beings who could look back and reconstruct this history. This is a satisfying story, a single thread from beginning to present, with us as the latest chapter. It gives the universe a history, a narrative structure, a sense of development and progress. But if the Big Bang wasn't the beginning, cosmic history becomes far more complex. In cyclic models, our Big Bang was one of infinitely many. There were previous universes with their own histories, their own stars, their own galaxies, perhaps their own life. These histories are lost to us, separated by the transitions between cycles, but they existed. The cosmic story didn't begin with our Big Bang, it extends infinitely into the past. In eternal inflation scenarios, our universe is one pocket in an infinite multiverse. Other pockets have their own histories unfolding in parallel with ours. Some might be older, some younger, some might have different physical constants, different structures, different possibilities. The cosmic story is not a single thread, but an infinite branching tree. In conformal cyclic cosmology, each aeon has its full history, from Big Bang-like beginning to heat-death-like end. Previous aeons had their own galaxies, their own stars, perhaps their own intelligent beings. Information from previous aeons might survive in subtle patterns, echoes of histories that played out before our aeon began. These are mind-expanding possibilities. The cosmic story we thought we knew 13.8 billion years from Big Bang to now might be just one chapter in an infinitely longer book. The universe might have a history so vast that our entire cosmic epoch is just a moment in it. The mysterious galaxy that James Webb found might be a messenger from this larger history, a relic from before our Big Bang, carrying information about epochs we cannot otherwise access. A fossil from a deeper past than we knew existed. Now let me consider what this means for the nature of existence itself. One of the deepest questions humans have asked is, why does anything exist at all? Why is there something rather than nothing? The Big Bang seemed to offer at least a partial answer. Existence began at the Big Bang. Before that, there was nothing, not even time, for nothing to exist in. The question, why something rather than nothing, became, why did the Big Bang happen? Which is still mysterious, but at least better defined. But if there was something before the Big Bang, this answer doesn't work. Existence didn't begin at the Big Bang. Existence was already ongoing in some form before the Big Bang occurred. The Big Bang was a transformation, not a creation from nothing. In cyclic models, existence is eternal. There was no first moment, no creation, no beginning. The universe has always existed, cycling through phases eternally. The question, why something rather than nothing, becomes unanswerable in the usual sense. Existence is not something that began, so there's no moment of creation to explain. This might seem unsatisfying. We might feel that we've just pushed the question back without answering it, but perhaps the question is itself flawed. Perhaps existence doesn't need an explanation. Perhaps something is the natural state, not nothing, and we should be more surprised if nothing existed than that something does. Philosophers have debated this for centuries. Some argue that existence is the default, that nothingness is unstable, impossible, or incoherent, and that something must exist of necessity. Others argue that existence is contingent, that things could have been otherwise, that our universe is one possibility among many, and that its existence requires explanation. The James Webb observation doesn't resolve this debate, but it adds new dimensions to it. If the universe extends infinitely into the past, if there was no first moment, if existence has always been, then the question of why existence began becomes meaningless. Existence didn't begin, it just is. Now let me explore the implications for the multiverse hypothesis. The idea that our universe might be one of many, a multiverse, has been controversial in cosmology. It's taken seriously by many theoretical physicists, dismissed as unscientific by others, and debated endlessly by philosophers. The James Webb observation, if it indicates a pre-Big Bang history, provides new evidence relevant to this debate. Several multiverse proposals naturally incorporate pre-Big Bang physics. Eternal inflation produces a multiverse of pocket universes, each with its own Big Bang. String theory's landscape of possible vacuum states might give rise to multiple universes with different properties. Cyclic models imply that our universe is one of infinitely many cycles, not a multiverse in space, but a multiverse in time. If the mysterious galaxy contains material or structure from before our Big Bang, it might be evidence that our universe is connected to something larger, a previous cycle, a parent universe, a pre-inflation state. This wouldn't prove the multiverse, but it would support frameworks in which the multiverse naturally arises. Conversely, if the observation can be explained without invoking pre-Big Bang physics, if it turns out to be an error, or if standard physics can accommodate it, then this particular argument for the multiverse would be weakened. The multiverse hypothesis is difficult to test because other universes, by definition, are not accessible to direct observation. But indirect evidence anomalies that point toward physics beyond our universe might be the best we can hope for. The James Webb observation might be exactly this kind of indirect evidence. Now let me consider the philosophical implications more broadly. The question of whether there was something before the Big Bang touches on some of the deepest issues in philosophy: the nature of time, the origin of existence, the structure of reality, the limits of human knowledge. If time extends infinitely into the past, certain philosophical positions become more plausible. Eternalism, the view that past, present, and future are equally real, fits naturally with an infinite past. The block universe, the idea that the entire history of the cosmos exists as a static four-dimensional structure, makes sense if that history extends without beginning. If the Big Bang was a transition rather than a creation, certain theological positions face challenges. Many religious traditions hold that the universe was created by a divine being. If the universe had no beginning, if it has existed eternally, then creation in the traditional sense didn't happen. This doesn't disprove the existence of God, but it does complicate certain conceptions of divine action. Some theologians have adapted to these possibilities. They argue that God could sustain an eternal universe in existence, that creation doesn't require a beginning, that divine action operates outside of time altogether. These are sophisticated positions that accommodate cosmological findings while preserving theological commitments. The philosophical implications extend to questions of meaning and purpose. In a universe with a clear beginning, a creation event, a first moment, there's a natural place to locate ultimate purpose. The universe was created for something, aimed at something, designed for something. In a universe without a beginning, an eternal cosmos cycling forever or extending infinitely into the past, purpose becomes harder to locate. Each cycle, each epoch, each phase might have local purposes, but there's no cosmic starting point where ultimate purpose could reside. This might seem disturbing, a universe without purpose, without meaning, without direction, but it can also be seen as liberating. If the universe doesn't come with built-in meaning, we're free to create our own. Our purposes, our values, our meanings are not given from outside. They're achievements, things we construct and maintain and develop. The philosophical landscape is vast, and I don't want to oversimplify. Brilliant thinkers have defended many different positions on these questions, and the James Webb observation doesn't definitively settle any of them. But it does shift the ground, adding new data to consider, new possibilities to evaluate, new constraints on what we can plausibly believe. Now let me discuss how scientists are working to test these ideas. Theoretical physics without experimental testing is speculation. The proposals I've discussed, cyclic universes, pre-Big Bang physics, loop quantum cosmology, conformal cyclic cosmology, are beautiful ideas, but they need to be tested against observations to be taken seriously as science. How can we test ideas about what happened before the Big Bang? The most promising avenue is the cosmic microwave background. The CMB is the oldest light in the universe, released about 380,000 years after the Big Bang. It carries information about the early universe, the density fluctuations that seeded all cosmic structure, the overall geometry of space, the composition of matter and energy. If there was a pre-Big Bang epoch, it might have left subtle imprints on the CMB. Different pre-Big Bang scenarios make different predictions about these imprints. Loop quantum cosmology predicts specific patterns in the CMB power spectrum deviations from the standard inflationary predictions at particular angular scales. So far, these deviations haven't been clearly detected, but they might be too small for current observations. Future CMB experiments with higher precision might reveal them. Conformal cyclic cosmology predicts concentric circles in the CMB rings of slightly different temperature caused by gravitational wave bursts from the previous aeon. Penrose and his collaborators have claimed to find such circles, but other researchers dispute the statistical significance. The debate continues, with more sophisticated analyses needed to settle it. String cosmology's pre-Big Bang scenario predicts a specific spectrum of primordial gravitational waves different from the inflationary prediction. Future gravitational wave observatories, particularly space-based ones like LISA, might detect this spectrum. The cyclic model predicts very low levels of primordial gravitational waves, much lower than standard inflation predicts. If we detect strong primordial gravitational waves, it would rule out or severely constrain the cyclic model. If we detect very weak or no primordial gravitational waves, it would be consistent with cyclic cosmology, though not proof of it. Beyond the CMB, there are other observational tests. The distribution of galaxies on large scales carries information about the early universe. Anomalies in this distribution, unexpected clustering, unexpected voids, unexpected correlations might point toward pre-Big Bang physics. The properties of early galaxies, like the one James Webb found, provide direct information about conditions in the young universe. More observations of extremely early galaxies, more detailed analysis of their stellar populations might reveal whether there's a systematic problem with the standard timeline. Gravitational waves from the early universe, if detected, would provide a completely new window onto pre-Big Bang physics. Gravitational waves are not absorbed or scattered like light. They propagate freely from their source. Primordial gravitational waves, produced in the first moments of the Big Bang or even before, would carry direct information about those epochs. Particle physics experiments might also be relevant. Some pre-Big Bang scenarios involve new particles or forces that might be detectable at particle colliders. Others predict modifications to known physics that might be testable in precision experiments. The path forward is observational and experimental. The theoretical frameworks exist multiple competing frameworks that make different predictions. What's needed is data to distinguish between them. Now let me consider what this discovery means for humanity's understanding of our place in the cosmos. For most of human history, we believe we were at the center of a small, young, purposeful universe. The Earth was the center of creation, created for our benefit, existing for a few thousand years. Science has progressively displaced us from this central position. The Earth orbits the Sun, not vice versa. The Sun is one of billions of stars in a galaxy. Our galaxy is one of hundreds of billions in the observable universe. The universe is 13.8 billion years old, and humans have existed for only a tiny fraction of that time. If the Big Bang wasn't the beginning, if the universe extends infinitely into the past, this displacement continues and deepens. Our cosmic epoch, the 13.8 billion years since our Big Bang, would be just one phase in an infinite history. Previous epochs had their own stories, their own structures, perhaps their own observers. We would be not only small in space, but small in time, recent arrivals in a cosmos that has existed forever. This might seem to diminish us further, to make our existence even more fleeting and insignificant, but it can also be seen differently. If the universe is eternal, if existence has no beginning, then the emergence of consciousness, of observers, of beings who can contemplate the cosmos might be inevitable. Given infinite time, anything that can happen will happen. The existence of beings like us might not be an unlikely accident, but a necessary feature of an eternal universe. In cyclic cosmologies, life might have arisen infinitely many times before, in previous cycles, in previous epochs. We might be the latest in an infinite sequence of conscious beings, each arising, flourishing, and passing away, followed by others. This could be seen as tragic or as beautiful, an eternal recurrence of awareness, an endless flowering of consciousness in the cosmic void. In the multiverse scenarios, life might exist in infinitely many forms across infinitely many universes. We would be not alone in existence, but part of a vast community of conscious beings, each in their own corner of the multiverse, each asking the same questions we ask. These are speculative visions, not scientific conclusions. But the James Webb observation opens doors to such speculation by suggesting that the simple story we thought we knew, universe begins, universe evolves, here we are, might be just a fragment of a larger truth. Now let me explore the methodological implications for cosmology as a science. Cosmology has always faced unique challenges. We have only one universe to observe. We can't do experiments on the cosmos. We can only watch and try to understand. The early universe is inaccessible to direct observation. We can only see its effects on the universe we observe today. These challenges become more acute if we're trying to understand what happened before the Big Bang. The pre-Big Bang epoch, if it exists, is separated from us by the Big Bang itself, an event that might have erased or transformed whatever came before. Information from before the Big Bang might be irretrievably lost, but perhaps not entirely lost. The theoretical frameworks I've discussed all suggest that some information might survive in subtle patterns in the CMB, in the properties of primordial fluctuations, in the characteristics of early structures like the mysterious galaxy. This is reminiscent of other situations in science where information seems lost but isn't entirely. Black holes were thought to destroy information, but the resolution of the information paradox suggests that information is preserved in subtle correlations in the Hawking radiation. The early Earth's history was thought to be erased by geological processes, but traces survive in ancient rocks and isotope ratios. Perhaps the pre-Big Bang history is similar. The Big Bang might have been a violent transition that destroyed most information about what came before, but not all. Fossils might survive. Echoes might persist. The mysterious galaxy might be one such fossil, a remnant that carries information from before the Big Bang into our current epoch. If so, cosmology's task becomes even more challenging, but also more exciting. We would be doing a kind of cosmic archaeology, sifting through the universe for traces of a history that mostly disappeared, reconstructing events that happened before time as we know it began. This is speculative, but it's the kind of speculation that drives science forward. The observation of something that shouldn't exist, a galaxy that seems to predate the Big Bang, forces us to speculate, to propose wild ideas, to test them against evidence. This is how science makes progress, especially in fields like cosmology, where the questions are so fundamental and the answers so difficult to obtain. Now, let me bring this exploration to a close by reflecting on what we've learned and what it means. The James Webb Space Telescope has found something extraordinary, a galaxy whose stellar population appears older than the age of the universe. This observation, if it holds up, challenges the foundation of our cosmological understanding. The standard model of cosmology, the Big Bang model that has been our framework for understanding the universe for nearly a century, might need fundamental revision. The Big Bang might not have been the beginning of time, but a transition from an earlier phase. The universe might be far older than 13.8 billion years, perhaps infinitely old. Several theoretical frameworks could accommodate this possibility. Loop quantum cosmology replaces the Big Bang singularity with a bounce, allowing time to extend into a pre-bounce era. String cosmology and brane models suggest that the Big Bang was a collision of higher dimensional objects with time existing before the collision. Cyclic models propose that the universe goes through endless cycles of expansion and contraction with no first cycle and no last. Conformal cyclic cosmology matches the end of one cosmic epoch to the beginning of the next in an eternal sequence. Each of these frameworks makes different predictions that can, in principle, be tested. The cosmic microwave background, gravitational waves, the properties of early galaxies all carry information that might distinguish between the possibilities. The philosophical implications are profound. If the Big Bang wasn't the beginning, then time might be eternal, extending infinitely into the past as well as the future. The question of why anything exists would take on new dimensions. Our place in cosmic history would be even smaller than we thought a brief moment in an infinite story. But the implications are also humbling and inspiring. The universe is stranger and more wonderful than we imagined. There might be depths of cosmic history we're only beginning to glimpse. The mysterious galaxy that James Webb found might be a messenger from those depths, a fossil from before our beginning, carrying information about epochs we never knew existed. This is what science does. It shows us that reality is bigger, deeper, more complex than our intuitions suggest. It challenges our assumptions, overturns our certainties, reveals new mysteries, even as it solves old ones. The question of what happened before the Big Bang has been asked for decades, often dismissed as meaningless, often treated as beyond the reach of science. But now we have an observation that forces us to take the question seriously. Something appears to exist that couldn't exist if the Big Bang was the absolute beginning. The answer is not yet clear. The observation might be wrong, the result of measurement error, model assumptions, or something we don't yet understand. Or the observation might be correct but explicable within standard physics through some mechanism we haven't yet identified. Or the observation might be pointing us toward genuinely new physics, toward a pre-Big Bang cosmos, toward a universe older and stranger than we knew. Time will tell. More observations will be made. More analyses will be performed. More theories will be proposed and tested. The scientific process will continue, grinding toward the truth, however surprising that truth might be. But for now, we can marvel at the possibility. A galaxy that existed before the Big Bang, a window into cosmic epochs we never knew existed, a message from before time began. The universe is not done surprising us. The cosmos is not done revealing its secrets. The story we thought we knew, the simple narrative from Big Bang to now, might be just a chapter in a much longer book, a book whose beginning we cannot see and whose ending we cannot imagine. This is the gift of observations like this one. They remind us how much we don't know. They humble our certainties. They open our minds to possibilities we hadn't considered. They show us that the universe is always bigger, always deeper, always more mysterious than we thought. James Webb has found something that shouldn't exist. And in doing so, it has shown us that the universe we thought we understood might be just the surface of something far more profound. The Big Bang might not have been the beginning. Time might extend beyond it. The cosmos might be older than we can comprehend, perhaps infinitely old, perhaps eternal. And we tiny conscious beings on a small planet around an ordinary star have somehow managed to glimpse this possibility. We have built instruments that can see across billions of years and billions of light years. We have developed theories that can contemplate the beginning of time and what might lie beyond. We have asked questions that our ancestors couldn't even formulate. This is the human achievement. Not just to exist, but to understand. Not just to live, but to wonder. Not just to see the stars, but to ask what they are and how they came to be. The galaxy that existed before the Big Bang, if it really did, is a testament to the universe's capacity to surprise us. But our ability to find it, to analyze it, to ask what it means, that's a testament to our own capacity to reach beyond ourselves, to seek truths that transcend our immediate experience, to pursue understanding wherever it leads. The universe might be eternal. The cosmos might have no beginning. Time might extend infinitely into the past. And we brief flickers of consciousness in this infinite expanse have somehow come to know this, have somehow looked back beyond the beginning, have somehow glimpsed the depths of cosmic time. This is what James Webb has given us. Not just an image, not just data, not just a puzzle to solve, but a window into the deepest nature of reality, a reality that might be far more profound than we ever dared to imagine. The Big Bang might not have been the beginning, and that possibility, that stunning, mind-expanding possibility, is perhaps the greatest discovery of all.